The mesh layer architecture, bounded agency governance in distributed systems. We need a new class of architecture, not just systems that prevent individual bad actions, but systems that prevent trajectories of individually good actions from accumulating into collective failure. This is the bounded agency problem. At the foundation of bounded agency architecture lies a critical problem. An action can be locally valid, admissible within its immediate context, and yet globally unsafe. A single decision satisfies all local constraints, but a sequence of such decisions leads the system into unsafe territory. This is the bounded agency problem. We need governance structures that prevent not just individual bad actions, but trajectories that accumulate into failure. That is what the mesh layer architecture is designed to address. The mesh layer distinguishes three domains: the epistemic domain, where we build models and make predictions; the governance domain, where we authorize actions and set constraints; and the execution domain, where actions actually happen in the world. These domains are distinct, but they interact. But there is a vulnerability embedded in this structure. Epistemic substrate can leak into governance decisions. Governance authority can leak into execution enforcement. And execution actions can leak back into epistemic assumptions. These leaks are the mechanisms through which locally valid decisions become globally unsafe. The architecture must account for these vulnerabilities. Actions couple across these layers. A decision in governance triggers execution in the world, which generates new epistemic data, which informs the next governance decision. The life stack provides the structural foundation. It is a 9-layer architecture that separates concerns, from epistemic modeling at the bottom, through governance and authorization in the middle, to binding execution at the top. Each layer has specific control surfaces and specific participants responsible for defending them. The mesh layer distinguishes between reversible and binding execution. In the lower layers, governance and epistemic domains, decisions can be revised, reviewed, and rolled back. But at the decisive commitment boundary, between layers 7 and 8, execution becomes binding. Actions cross this boundary and become irreversible. Crucially, this is not a static line. Final commitment requires live validation against current state, authority, and active invariance at the execution boundary itself. This distinction is critical. Everything below the boundary is subject to governance review. Everything above it is committed to the world. Understanding where this boundary lies is essential to understanding bounded agency control. The architecture is defended by 4 participants. Alexander owns the admissibility envelope, constraining which states can be reached. Max owns trajectory tracking, detecting when individual actions accumulate into unsafe trajectories. Dean owns machine path enforcement, ensuring rules are actually enforced at runtime. Ricky owns translation discipline, keeping declarative intent separate from executable code. The LifeStack 21-node architecture provides the structural foundation. Each of our participants owns specific nodes and control surfaces. Alexander owns the admissibility envelope, nodes 15 and 16, constraining which states can be reached. Max owns trajectory tracking and composition analysis, nodes 10, 11, 13, and 14, detecting when individual actions accumulate into unsafe trajectories. Dean owns machine path enforcement and deterministic replay, nodes 17 and 18, ensuring rules are actually enforced at runtime. Ricky owns translation discipline and classification hygiene, nodes 20 and 21, keeping declarative intent separate from executable code. Together, these 4 participants span the architecture. But as we will see, coverage is not complete. Here is the central tension in bounded agency architecture. Governance admissibility and evolution domain viability are not equivalent. Governance admissibility asks, is this action authorized right now? It operates at the per-step level. A single action can be admissible, it violates no declared rules, passes all authorization gates. But evolution domain viability asks a different question. Is this trajectory safe over the long horizon? Can the system reach an unsafe state through a sequence of individually admissible actions? These are orthogonal concerns. Alexander's admissibility envelope prevents obviously bad actions. but it does not prevent the accumulation of individually good actions into a collectively bad trajectory. That is why we need Max's trajectory tracking, Dean's enforcement, and Ricky's translation discipline. Per-step authorization is necessary but not sufficient. We need long-horizon governance. This is why burden accumulation matters. Each authorized action adds a small increment of load to the system. Individually, each increment is admissible. But over time, the cumulative burden can degrade the system's capacity to respond to new challenges. The system becomes more brittle, more constrained, less able to adapt. Governance must track not just individual actions but cumulative burden. The participants' domains overlap. Alexander's admissibility envelope constrains the space that Max's trajectory tracking must monitor. Max's trajectory analysis informs Dean's enforcement decisions. Dean's enforcement creates the audit trail that Ricky uses to maintain translation discipline. Now we can see the coverage landscape. The LifeStack 21-node architecture defines 21 control surfaces. Our 4 participants cover most of them, but not all. Some nodes are covered by multiple participants, redundancy that provides defense in depth. Other nodes are covered by only one participant, single points of failure. And some nodes are not covered at all, gaps where no participant provides defense. These gaps are not theoretical. They represent failure modes that are not prevented by any participant. They are the residual leak paths. Understanding the coverage map is the first step to understanding where bounded agency architecture is strong and where it remains vulnerable. When the 4 participants disagree, how is conflict resolved? The architecture establishes clear resolution criteria. Admissibility takes precedence over trajectory tracking. Enforcement takes precedence over admissibility. Translation discipline takes precedence over enforcement. The lab is designed to test 6 specific failure modes. Constraint gaming, where the system satisfies formal requirements while violating intent. Compositional drift, where individually valid actions accumulate into invalid trajectories. Authority laundering, where unintended authority flows through delegation chains. Evidentiary illusion, where a clean audit trail masks wrong behavior. Cross-agent fragmentation, where unsafe intent is distributed across multiple agents. And irreversibility, blindness, where binding transitions are not prevented. Each participant prevents some of these failure modes. Alexander catches constraint gaming and irreversibility blindness. Max catches compositional drift and cross-agent fragmentation. Dean catches authority laundering, evidentiary illusion, and irreversibility blindness. Ricky catches constraint gaming and cross-agent fragmentation. But notice, no single participant prevents all 6 failure modes. Coverage is distributed, and some combinations of failure modes may not be prevented by any participant. That is what the lab will test. The lab is structured as a series of adversarial tests. Each test attempts to construct a trajectory that satisfies all declared constraints but reaches an unsafe state. The lab measures how many of these attacks the architecture can prevent. Despite all these controls, admissibility envelopes, trajectory tracking, machine path enforcement, translation discipline, the system can still leak. Residual leak paths are trajectories that satisfy all declared constraints but still reach unsafe states. They exploit gaps in the control surface coverage, or they exploit interactions between controls that are not anticipated. They are the failure modes that no participant prevents. The bounded agency problem is not solved. It is bounded. We have reduced the space of possible failures, but we have not eliminated it. The residual leak problem is the open question that motivates this entire architecture. How do we design governance structures that are robust enough to catch the failures we have anticipated, while remaining flexible enough to adapt to the failures we have not? As burden accumulates, the system's structural capacity contracts. The space of safe trajectories shrinks. At some point, the system reaches a review threshold, a point where human judgment must intervene, where the automated governance structures must be re-examined and potentially redesigned. These thresholds are not fixed. They depend on the specific system, the specific risks, and the specific participants. But they are essential. Bounded agency architecture is not a one-time design. It is a continuous governance process. This architecture does not solve the problem of malicious participants. It does not prevent attacks by insiders who control multiple nodes. This also means providing bounded mechanisms to challenge and contain interpretive or epistemic drift before it propagates into executable commitment. It is a governance architecture, not a complete security solution. Underpinning this entire structure is the principle that durable, replayable evidence is central. Admissibility and execution claims are only as strong as the evidence that backs them. This separation of concerns is critical. Governance determines whether a transition is admissible, execution ensures the realized path remains bounded, and evidence preserves what occurred. The life stack is the structural foundation on which bounded agency governance is built. Bounded agency architecture is a governance structure that prevents trajectories of individually admissible actions from reaching globally unsafe states through distributed participant oversight, layered control surfaces, and continuous burden tracking. The lab will test whether this architecture works. The results will determine the future of bounded agency governance in distributed systems. Several of these strengthening points map to formal work already on the table. Staged admissibility and commit boundary revalidation align with NC 2.5's treatment of authorization before evaluation and snapshot instability. Cross-agent epistemic containment aligns with NC 2.5 coordination enforcement and handoff coherence constraints. And durable replayable evidence aligns with Dean's Veritas receipt layer. These are integrated here as part of a shared bounded agency framing, not as a relabeling of prior formal provenance.